Hello students, in this video we will work the second set of problems in chapter 2 of our MCAT prep course, and these are problems involving energy and power. So the first problem, it poses a physical situation where a meteorite collides with the atmosphere of Jupiter, and so you have, here's Jupiter if you like, here's the great red spot, and here's the meteor coming in. And what it says is that the meteor is initially moving at 20 kilometers per second, which is actually not all that fast for a meteor. And then it says that it travels a distance of 100 kilometers and then disintegrates. And what you are asked is, what is the average force on the meteor, exerted on the meteor by the atmosphere? So you may know Jupiter is what's called a gas giant. It's a planet that, rather than having a solid surface, a thin atmosphere and then a solid surface like the Earth, it has a very thick atmosphere that merges continuously into like a liquid type atmosphere still. It's just this very thick gas and then into liquid, and it has a rocky core at the center, it's believed, but this is very deep under the surface. It doesn't have a, solid surface like Earth does. And so this meteorite will penetrate into the planet, and as it's penetrating into the planet, there will be wind resistance, which is pushing back the other way. So this here, the meteorite penetrates here, and then there's wind resistance, and that's the force that's being exerted, and that's the average force that they are asking you for. There was actually an event that happened some years ago where a comet struck Saturn or Jupiter on one side, and you can actually see the evidence, partly coming out the other side. It messed up the atmosphere that much, and so that gave some more idea of what the interior of Jupiter is actually like. But here, for the purposes of the problem, I've converted the kilometers per second and the kilometers here to meters. So this one here, this 2 times 10 to the 4th was supposed to be meters per second, and the 1 times 10 to the 5th was supposed to be meters. So a kilometer means 10 to the 3rd in both of these cases. So you get a 10 to the 4th for the speed by taking the 10 to the 3rd. So that would be kilometers per second. That converts the kilometers per second to meters per second. And then you multiply that by 20. So there's one more zero. So that makes it 10 to the 4th. And then there's a 2 coming from this 2 here. And then similarly, the 100 kilometers, well, a kilometer is 10 to the 3rd meters. And then you add 2 more zeros to change the 10 to the 3rd to 10 to the 5th. So that's what you get here. Now, this problem, they expect you to assume something which they don't tell you in the problem, and that is that the meteorite comes to a stop before it disintegrates. Now, that's actually not a very good assumption. Typically, a meteorite will disintegrate, it will explode in the atmosphere long before it is even close to coming to a stop. So that's kind of, and they don't tell you that in the problem, so in a way it's misleading. But if you didn't assume it comes to a stop, you would have no way of solving the problem. So you have to assume that. Okay, so let's assume that. What does that tell us then? Well, it tells us, and I'm going to erase the picture here. It tells us that we have a change in velocity from 2 times 10 to the 4th meters per second to 0 meters per second that's occurring over a distance of 1 times 10 to the 5th meters. Now, what you're going to want to do is, so we're being asked for an average force that's being exerted by the atmosphere. So we're going to want to use, that work equals force times distance. And we're going to find the force by finding the acceleration. The acceleration is the change in velocity. And we're going to find the work by the change in velocity from the initial striking the atmosphere to zero. So this is a little bit complicated, I guess. So let me go through the details. So the work W done on the meteorite is the same as the change in kinetic energy. I don't know why I left out my K here. Work done on meteorite is the change in kinetic energy. Now, at first, when it's going at 20 kilometers per second, the kinetic energy, I guess I'll be consistent and continue with my scientific notation. I'll call the 20 kilometers per second the 2 times 10 to the 4th meters per second here. The kinetic energy, remember, K is 1/2 mv squared. Now, the m is 1 kilogram. That's the first thing I wrote here. So that's going to be 1/2 times 1 times v, that's this, 2 times 10 to the 4th squared. So that's going to come out to be 1/2, 1, and then this is 4 times 10 to the 8th. The 1/2 and the 1 and the 4 will all go together to give you 2. So this is going to be 2 times 10 to the 8th. That's the kinetic energy, and so this would be measured in joules. That's the kinetic energy when it first hits the atmosphere. Now, when it stops and disintegrates, you know, they say it disintegrates here, but it's come to a stop before disintegrating. So this is 0 meters per second, and so that's going to be a 0 kinetic energy. So this change in kinetic energy is this number here, 2 times 10 to the 8th joules. And since I've calculated this here, I can erase this here now. Okay, well, so if I want to now use this work equals force times distance, I can say I've got the work now, so I can say 2 times 10 to the 8th, and I'll fudge in the units at the end, equals force, this is what we're wanting to solve for, the average force, times the distance. And I have the distance here. This is 1 times 10 to the 5th. So I can rearrange this and write the force, which is what I'm looking for, is 2 times 10 to the 8th over 1 times 10 to the 5th. Now, you know laws of exponents. I have the 10 to the 8th here, the 10 to the 5th here. Those cancel to give me a 10 to the 3rd, and the 2 stays by itself. So this is going to be 2 times 10 to the 3rd. This is force, and this is going to be in newtons. And so that will be your answer, and that's answer choice A. So that was a little bit of an involved problem. Not only was it involved, but it also required you to make an assumption which was not at all obvious. So that was a little bit intimidating of a problem, I guess. Okay, this next one, I guess I forgot to mark. It's funny, I can never get my numbers up here right. Either I keep the same number for too long, or else I forget to write it at all. But here it's a problem 34. It says you stack up blocks starting on the surface of the Earth, and these are blocks of the same size, and you continue these up forever, which is an idealism, I guess. I mean, obviously it wouldn't go on forever. If it did, it'd get into the galaxy and get close to other stars and all this kind of thing. So you're supposed to ignore what's happening outside the Earth and the solar system and galaxy and all this. You just assume you make a very high stack of blocks. And so what the problem asks you is, do the blocks at the bottom, so these are bottom blocks, do they have more or less gravitational potential energy, that's the UG, than top blocks. So the top blocks are up here, and these blocks are supposed to go on, theoretically they go on forever going up there. And the book actually gives a fairly long explanation. It's about that long of why the blocks down here have lower gravitational potential energy. And I guess they're getting into more details than they really discuss in the text. It's like the force of gravity changes as you move away from the Earth, if you move far enough away from the Earth. But to get the right answer, all you have to do is use the easy approximation of gravitational potential energy as mgh. So if I have a particular block here at height h, then the gravitational potential energy, that would be mgh. And the bigger h gets, the bigger mgh gets. So the bottom blocks have less potential energy than the top blocks, and that's answer choice A. Okay.